Good afternoon, class. Today we're continuing with main memory, that is to say, main memory management. Here are today's topics. I'll be going through the ARM slides, but skipping that material, and another look at the chapter objectives. Paging is the foundation of memory management today. So the idea is that physical memory is broken into frames that are size is a power of 2 bytes. Logical memory is broken up into pages, which are the same size as frames. So the memory management unit provides a mapping between pages and frames, with that mapping being performed by a page table. Breaking memory into the fixed-sized frames solves the external fragmentation problem. Having fixed-size pages can cause some internal fragmentation, and on average the amount of fragmentation will be half the size of a page. And splitting processes logical address space into pages. Those pages can be anywhere in memory, so processes memory space need not be in contiguous memory anymore, as we'll see. So here's what a logical address looks like. High order bits are the page number, and the low order bits are the page offset. So if the page offset is n bits, then that implies that the page size is 2 to the n bytes, and the remaining number of bits are the page number. Here that's m minus n, so that implies that the page table has m minus n entries in it. And m here is the number of bits in a logical address. So here's what's going on in an MMU. The CPU generates a logical address consisting of the page number and the page offset. The page number is used to index into the page table, producing a frame number. That frame number then is appended to the offset to give us the physical address. So here's a figure illustrating it. So we have a logical address space of 4 pages and the page table. So page 0 maps to frame 1, page 1 maps to frame 4, etc. So you can see that the pages can be placed into any available frames. Now this is illustrating the same thing using byte level addresses. Here we see 2 of the considerations necessary for taking into account or for deciding what page size should be. So if we want to reduce fragmentation, we want a small frame size, but a small frame size implies a small page size, which means that the page table will be larger. So that's the trade-off we have between internal fragmentation and page table size. And for large address spaces, today we have 64-bit address spaces, the page table itself can become absolutely huge. This slide demonstrates frame management. When a process is created, here we have a process with a logical address space of 4 pages and a list of free frames. The operating system allocates 4 frames and then constructs the process's page table. And it obviously updates the free frame list. So the page table itself is kept in main memory. A page table base register points to the base. of the page table, and the length register gives the length of the page table. A consequence of this now is that a single memory reference requires two memory operations, one to reference the page table and the second to perform the actual memory read or write. That can be time consuming, so special type of a cache, a translation look-aside buffer, is used to cache portions of the page table to eliminate that second memory access. Now when a context switch occurs, all of those cached entries in the TLB would be invalidated because now we're working with the address space of a different process. But given the frequency at which context switches occur and the way processes tend to use memory, it's not always advantageous to purge the translation look-aside buffer. So a technique that can be used is to assign an address space identifier. You can think of it as a PID, a process identifier at the hardware level to the TLB entries. So that that can be used to distinguish between different processes entries in the TLB, so that the TLB doesn't have to be flushed. TLB specifically and caches in general are a form of associative memory. So rather than providing an index with an associative memory, you provide part of the content, and then all of the memory cells are searched in parallel for the rest of the content. So with regard to a translation look-aside buffer, the page number is provided. The page number is stored in each TLB entry. So these TLB entries are searched in parallel, and if there's a hit, meaning that one of the TLB entries contains that page number, then the corresponding frame number pops out. If so, a hit is when the page is found. Correspondingly, if the page is not found, that's referred to as a miss. So this illustrates it. Upon the CPU generating a logical address, the page number is associatively searched in the TLB. If we get a hit, then that frame number from the TLB is used. Otherwise, if we get a miss, then we perform a memory access to access the corresponding entry in the page table, which would likely be placed into the TLB at that point, and then the frame number from the page table is used for the physical address. So without a TLB, the effective access time is two memory accesses. With a TLB, then we can compute the effective access time knowing two things: what the hit rate is. So this is a number between a real number between 0 and 1, and the time for the TLB lookup, which for the equation we have below, this will be expressed as some fraction of a memory access time. So the effective access time is the weighted average of a TLB hit. So remember, this is the hit rate, and this is the memory access time, 1 for the final actual memory access, and epsilon here for the TLB access time, with the weighted average of a miss. Right, so the miss rate is 1 minus the hit rate. Then the two accesses, one to reference the page table, and then one for the final memory reference. And then in this model, we're assuming that we don't do the, or that we perform the TLB lookup and then perform the page table access. So that's where the 2 plus epsilon comes from. Some architectures could conceivably perform the TLB search in parallel with starting a page table in memory reference, but that could lead to other problems. Then in these two examples, note that they're using the actual memory access times in nanoseconds rather than this figure of 1 here. So here you see 2 applications of this equation. So control bits in page table entries can be used to provide memory protection, such as a valid, invalid bit. And also the page table length register would be used to limit the size of the page table. Without the page table length register, the entire page table would have to be in memory, and as we'll be seeing, that can be a problem. So here's a small example. Let's assume that the page number field in a logical address is 3 bits, meaning that the page table would have 8 entries, but we have a process that only needs 6 pages. So the valid bit would be set as shown here. This mechanism of paging allows processes to share pages. All we have to do is to map page table entries in the page tables of 2 or more processes to the same frames in memory. So this can result in savings because such things as code don't need to be writable. So processes can share code segments, but obviously data that processes aren't sharing shouldn't be in shared pages, but this is the mechanism that processes can use when they implement shared memory for communication and synchronization purposes. So here's a small example. We have 3 processes running an editor program that requires three pages. So there are the editor, editor, and then looking at the page tables for these 3 processes, you can see that those pages that the editor are using are being mapped into the same frame, but that the data being edited for each process is mapped into a unique frame. Now we're talking about the implications of size of a page table. So if we have a 32-bit logical address with a page size of 4K bytes, so that implies that the page offset is 12 bits, then that leaves us with a page number field of 20 bits, which is a million entries. And assuming that each entry in the page table is 4 bytes, the page table then is 4 megabytes. Today, that's not a whole lot of memory, but with the way systems operate, we wouldn't want to have to allocate that much contiguous memory, which, given that the page table is indexed, that's an assumption that we've been using all along. So next we're going to look at a few ways of reducing the size of the page table or splitting it up into pieces so that we can page the page table. All right, we'll start with hierarchical page tables first. As an example, we'll use a 2-level page table, where the inner pages can be paged, as we'll see. So here's the idea. Here we have the final pages, the inner page table, and the number of bits that are used to select this, as we'll see, is chosen to ensure that one of these page tables fits into a single page, and then finally the outer page table. All right, so let's assume that we have these specifications. So a 32-bit address with a 1K page size. So we know right away that the page offset is 10 bits, giving us a page number of a single level page table number of 22 bits. So I just realized that there is a problem with the way the bits are allocated for these fields. Why don't you pause here and think about what the problem is. What we actually want is a page size of 4K bytes. So the page number is 20 bits. I can't change these numbers here, so this should be 10, this should be 10, and then with the page size of 4K, this is 12 bits. And as I changed here, the page offset is 12 bits. So the inner page table index is 10 bits. The outer page table index is 10 bits. The reason for this is with a 4K page size, an inner page table entry being 10 bits, there are 1024 of those, or 1K. So by selecting a page size of 4K, that gives us 4 bytes per inner page table entry. If we had left, remember that's a 12 there, if we left it 10 and 10, then we only have 1 byte per inner page table entry, and that's not enough. And remember, the reason we want the inner page table to fit into a 4K page is so that we can page the page table. So the outer page table then will index to the, or will point to the individual inner page table entries, allowing them to be distributed throughout memory. So now, rather than a single page table of 20 bits, we have the page second level table, which is non-contiguous, and the outer page table, which is contiguous, but now is only 1024 entries long. So here's how an address translation would work. Remember, we still have the page table base register that points to the base of the outer page table and the page table limit register. So the outer page number is used to index into the outer page table. That gives us a base of one of the inner page tables, and the inner page table number gives us an index into that particular inner page table, and that entry then gives us frame number, which when combined with the page offset gives us the physical memory address. Now note that 1 memory access, 2 memory accesses, 3 memory accesses. So again, we'll need to use some sort of a TLB scheme in order to minimize the effective access time. So that previous scheme pretty much solved the problem for 32-bit logical address spaces, but what about 64-bit logical address spaces? Using a two-level scheme, the outer page table is 2 to the 42 entries, which is a bit prohibitive. So what do we do now? Well, we could go to a 3-level paging scheme, but then we still have 2 to the 32 entries on the outermost page table. That's not going to work. Well, this is a search problem. So one of the commonly used solutions to search problems is hashing. So why don't we hash on the page number and see what happens. So here's the idea. Take a page number, hash it, use the hash value as an index into a hash table, um, select the appropriate entry, and then linearly search through a list looking for a matching entry. Take the frame number, and we have the physical address. Given the sparsity of most address spaces, this will be pretty efficient most of the time. Another solution is to use what's known as an inverted page table. So a page table has an entry for each logical page. An inverted page table has one entry for each physical frame. We'll see an illustration of this momentarily. I'll pause here for a second so you can hit pause to look at these bullet points. One of the complicating factors here is that the way an inverted page table works, it's a mapping from a frame to a process. So implementing shared memory is a little complicated when using an inverted page table. So the inverted page table is searched. So ideally, we would use an associative memory for this. You can see that it's indexed here by the frame number, and the entries are an address space identifier or a PID, indicating the process that has been allocated the frame along with a page number. So a logical address consists of the usual page offset, page number, and a PID, and then the inverted page table is searched associatively using PID and the page number. When we get a hit, the index into the page table is used as the frame number, and that gives us the physical address. I'm going to skip the material on the Spark, so I'm also skipping this. As an example, I'll talk about 32-bit and 64-bit addressing in x86. It's not uncommon for segmentation and paging to be combined in a way where logical addresses are to segments, and then the segments are broken into pages. So that's what we'll discuss first for 32-bit addressing in x86. So remember, with segmented addressing, an address is an ordered pair consisting of a segment number and a segment offset. So with x86, the segment number is broken into fields. The 2-bit P field is protection. G here is used for referencing the global descriptor table if G is 1, or the local descriptor table if G is 0. And then the segment field, this is the segment number field. Remember, what pops out of the segment table is the base address of the segment. So then the segment offset is added to that, right? And Intel calls that a linear address, which is then passed on to the paging unit. So the linear address coming from the segmentation unit is treated as a 2-level paged address, as shown here, and assuming a page size of 4K bytes. So here's how the segmentation unit does its work. Here's how the paging unit works. Note that x86 has 2 page sizes, 4K bytes or 4 megabytes. There is a bit in the page table entry that indicates whether a page is 4K or 4 megs. If the page is 4 megs, then the lower 32 bits are used as the offset. Otherwise, if the page is 4K, then these 10 bits are the offset into the inner page table entry, or the inner page table. And of course, the page directory field, here is the offset into this page directory, and the entries give the base addresses of the page tables. I'm going to skip page address extensions. I suspect you've seen enough complexity for now. All right, so for the 64-bit addressing, one of the simplifications off the bat are to use only 48 bits, and then to use a 4-level paging hierarchy to try to get some order and some organization to the paging table. I'm going to skip ARM, and that completes Chapter 8.